Bismillahirrahmanirrahim. Start with the name of Allah, the most gracious and the most merciful. My name is Isha Shafiq and I am from the Department of PS Chemistry. The topic of my presentation for the practical is chemical fingerprinting of space debris or returned particles microscale residue analysis. So let's start it. First point is the aim. The aim is to perform microscale chemical fingerprinting of space debris or return particulate samples in order to determine their morphological, elemental, molecular, and organic composition, and to establish unique chemical signatures for source identification and material characterization. Theory. Introduction to chemical fingerprinting of space debris. Space debris, micrometeorite, and returned spacecraft particles often carry valuable information about their origin, interaction with the space environment, and material composition. Chemical fingerprinting involves the identification and characterization of these residues as a microscale, enabling researchers to trace the source material, assess contamination, and study the effects of hypervelocity impacts, thermal cycling, and radiation exposure in space. Importance of space microscale analysis. The particles collected from space missions or debris samples are typically extremely small, micron to submicron scale, and heterogeneous. Conventional bulk analysis is insufficient. Microscale analytical technique allow high resolution characterization, ensuring that even trace residues can be detected and identified. Microscale chemical fingerprinting is critical for determining the material origin, aluminum alloy, polymers, composites, and paint layers. Detecting contamination from the collection process and or spacecraft environment. Understanding material degradation or space modification due to space exposure, supporting forensic studies of hypervelocity impacts or collision events. Apparatus and material. First we will discuss the apparatus. We use scanning electron microscope with energy dispersive X-ray spectroscopy, which is EDS, micro Raman spectrometer, gas chromatography, mass spectrometer GCMS, and optical microscope, sputter coating unit, ultrasonic bath, analytical balance, laminar flow hood, or clean workspace. Materials. Space debris or return particulate matters or simulated impact residues, SEM stubs and conductive carbon tape, gold or platinum coating material, high purity organic solvents, hexanes, dichloromethane, and methanol, glass slides or silicon wafers, deionized water, protective equipment, which is gloves, lab coats, and safety goggles. Description of techniques. Scanning electron microscopy, SEM with energy dispersive X-ray spectroscopy, which is ADS. Principle is SEM uses a focused beam of high energy electron to scan the surface of a sample. The interaction of electrons with the sample generates secondary electrons, backscattered electrons, and characteristics X-rays. Secondary electrons produce higher resolution images of space morphology. Backscattered electrons provide contrast based on atomic number. EDS defects or detects characteristics X-rays emitted from elements in the sample, allowing elements identification and semi-quantitative analysis. Energy dispersive X-ray spectroscopy, EDS. When the electron beam hits the sample, it can eject inner shell electrons from atoms. Outer shell electrons fill these vacancies, emitting X-ray with energies characteristics of the element. EDS detect these X-rays to determine the elemental composition. Advantages are high spatial resolution, nanometer scale, ability to combine morphological and elemental information, minimal space sample destruction if properly prepared. Next, our technique is micro-Raman spectroscopy. Its principle is Raman spectroscopy is based on inelastic scattering of monochromatic light, usually from a laser. When photons interact with molecules, a small fraction is scattered at different energies corresponding to vibrational modes of chemical bonds. The Raman spectrum serves as a molecular fingerprint of the sample, identifying chemical structures. Advantages are non-destructive analysis, micron scale spatial resolution can detect both organic and inorganic residues. Sample preparation, minimal particles can be mounted directly on clean glass slides or substrates. Next, our point is GCMS, gas chromatography mass spectrometry. Principle is gas chromatography separates volatile and semi-volatile compounds in a mixture based on their interaction with the stationary phase of a chromatographic column. Mass spectrometry ionizes separated compound and measured their charge mass to charge ratio m over z, producing a spectrum that is characteristic of the compound structure. Application in chemical fingerprinting, identification of organic residues such as lubricants, adhesives, or polymer degradation products, quantification of trace contaminants. Comparison of chemical profiles to identify the source materials. Advantages are high sensitivity for trace organics, provide both qualitative and quantitative information, can handle complex mixtures, sample preparation, dissolution or extraction of residues in appropriate organic solvents. Filtration or concentration may be required for very small samples. Next, our technique is which is optional. Isotopic analysis, for example, SIMS, LA, ICP, MS, measures isotopic ratios of element in the sample, useful for distinguishing cosmic origin, contamination, or material provenance. Optical microscopy, preliminary inspection to select suitable particles for advanced techniques. Last but not the least, experimental procedure. Sample preparation, collection of particles, obtain microscale particles from returned spacecraft samples, simulated hypervelocity impact residues or cosmic dust, handle particles carefully using micro tweezers or micro manipulators to avoid contamination. Cleaning and mounting, rinse sample gently with deionized water or suitable solvent to remove loose debris. Dry sample used under a laminar flow hood to prevent contamination. Mount each particle on a clean SEM stub using conductive carbon tape. Coating for SEM EDS. If the particle is non-conductive, apply a thin layer of gold or platinum using a sputter coater to prevent charging during SEM imaging. SEM EDS analysis, insert the mounted sample into the SEM chamber, evacuate the chamber to achieve high vacuum, adjust electron beam parameters, accelerate voltage 5 to 20 kilowatt, spot size optimized for particle size, scan the particle surface to capture high resolution image of morphology and microstructure, activate EDS to detect characteristic X-ray and obtain elemental composition, record spectra and generate elemental maps showing distribution of major and trace elements. Micro-Raman spectroscopy, place the particle on a clean glass slide or silicon wafer. Focus the Raman laser on the particle using a microscope attachment. Adjust the laser power to prevent sample heating or degradation. Collect Raman spectra over a suitable wave number range, for example 100 to 3500 per centimeter. Analyze spectra to identify chemical bond, polymer types, mineral phases, or carbonaceous compounds. GCMS analysis for organic residues, extract organic by extract organics by immersing the particle in a small volume of organic solvent, hexane, dichloromethane, and methanol, which we discussed. Sonicate the solution in an ultrasonic bath for 5 to 10 minutes to improve extraction. Filter or centrifuge the extract to remove solids. Concentrate the extract using a rotatory evaporator if necessary. Inject a small volume 1 to 2 microliter into the GCMS system. Separate compounds using the GC column and detect them using the mass spectrometer. Compare mass spectra with reference libraries to identify organic compounds. Data analysis and interpretation. Combine SEM, EDS, Raman, and GCMS results data to generate a complete chemical fingerprint of each particle. Compare elemental and molecular profiles with known spacecraft materials, cosmic dust, or contamination sources. Identify the likely origin of each particle, for example, spacecraft debris, micrometeorite contamination. Prepare tables, spectra, and micrographs for reporting. These are the observations: SEM, irregular morphology, melt features and microcraters; EDS, Al, aluminium, Fe, iron, silicon, magnesium, titanium, and oxygen with trace metals; microraman, polymer, carbonaceous metals and silicates; GCMS, hydrocarbons, polymer fragments, and lubricants. These observations confirm that microscale analytical techniques effectively reveal morphological, elemental, and molecular characteristics, enabling reliable chemical fingerprinting and source attribution of space debris and return particles. So the calculations are elemental weight percentage calculation, EDS analysis. EDS provide X-ray intensities for detected elements. Elemental composition is calculated using ZAF. Corrected intensity ratios formula is given below, where I iota is equals to X-ray intensity of I. Zi is equals to atomic number correction, accounts for electron backscattering and stopping power. Ai is the absorption correction, accounts for X-ray absorption within the sample. Fi is the fluorescence correction, account for secondary X-ray excitation. N is the total number of detected elements. Next, our formula is our formula is Ii is equals to Zi, Ai, and Fi. Here we just take the I common in ZAF above and below, where ZAF is equals to Zi, Ai, and Fi. ZAF is equals to atomic number, absorption, and fluorescence correction factor. Okay. Example calculations. Aluminium corrected intensity is 620, oxygen is 310, and silicon is 70. Total intensity is equal to 1000 if we get the percentage. For aluminium is 62, for oxygen is 31%, and for silicon is 7%. Atomic percentage calculation. Atomic percent provide insight into the elemental ratios. Formula is atomic concentration is equals to Wi over Ai over sigma W over A multiplied by 100. So we put the values. W is the weight and A is the atomic weight. We put the values and we get the results. Here we put the values in the formula and we get the result for aluminium and oxygen. Raman shift calculations. Raman shift is calculated as the difference between the incident and scattered photon numbers. Delta mu is equals to mu naught minus mu s, where mu naught is equals to incident laser frequency and mu s is equals to scattered frequency. If we put the values, if laser wavelength is equals to 532 centimeter, we get the value for mu naught. If scatter wavelength at 16,200 per centimeter, we get the value for mu naught. We get the value for delta mu. This correspond to the C single bond H stretching vibration indicating polymeric residues. Degree to carbon disorder, Raman D over G ratio, used to assess carbonaceous material origin. Formula is D over G ratio is equals to ID over IG, where ID is equals to intensity of D band, which is approximately 1350 per centimeter, and IG is equals to intensity of G band, which is approximately 1580 per centimeter. Example is, if ID is 820 and IG is 610, we get the ratio for this 1.34. Higher DG ratio indicate amorphous or impact altered carbon typical of space debris. GCMS compound concentration calculations. Formula is concentration mu G over micro G over G is equals to AS over ASTD multiplied by CSTD, where AS is equals to sample peak area, ASTD is equals to standard peak area, and CSTD is equals to known concentration of standard. Example is given below. These are the values for AS, ASTD and CSTD. We put the values in the formula and we get the result 9.0 microgram per gram. Particle size measurement, SEM image analysis. Formula is atomic actual size is equals to measured length on image over magnification. These are the values for measured length is equals to 6.0 mm, magnification is 20,000 times, and particle size is we get that size by dividing the values 0.3 micrometer. Source attribution index qualitative calculations. SAI is equal to anthropogenic element plus polymer over silicate plus cosmic indicators. SAI is greater than 1 spacecraft debris, and if SAI is less than 1 natural micrometeorite. Result from calculations. The calculated elemental composition, Raman peak ratios, organic compound concentration, and particle size collectively confirm that the analyzed samples exhibit distinct chemical fingerprinting, allowing reliable differentiation between spacecraft-derived debris and extraterrestrial particles. Sources of errors are: despite the use of advanced analytical techniques, certain experimental and instrumental factors may introduce errors or uncertainties in the chemical fingerprinting of space debris and returned particles. Sample contamination. Contamination from handling, storage, or mounting materials, carbon tape, solvents, or tweezers can alter elemental or organic signatures. Airborne particulates or laboratory dust may introduce false positive organic or inorganic signals. Limited sample size. Microscale particles provide very small analyte volume, reducing signal intensity and increasing uncertainty. Heterogeneous particles may yield non-representative results if only a small origin is analyzed. SEM EDS measurement errors. EDS has limited sensitivity for light elements, for example C and O, leading to underestimation. Surface roughness and particle geometry can affect X-ray emission and detection efficiency. Conductive coating, AU over PD, gold over platinum, may obscure or overlap elemental peaks. Raman spectroscopy errors. Fluorescence from organic material can mask Raman signals. Excessive laser power may cause thermal degradation or structural change in sensitive materials. Misalignment or poor focusing can reduce spectral accuracy. GCMS analytical errors. Incomplete solvent extraction may result in underestimation of organic compounds. Thermal decomposition during GC analysis can modify original compounds. Column bleed or background noise may interfere with trace level detection. Instrument calibration and drift. Improper calibration of SEM, Raman spectrometer, or GCMS can cause systematic error. Instrumental drift over time affect intensity, peak positioning, and quantitative accuracy. Data interpretation uncertainty. Overlapping elemental or molecular signatures may lead to ambiguous source attribution. Reliance or reliance on reference databases may introduce errors if materials are not well represented in libraries. Environmental factors, temperature fluctuations and vibration can affect instrument stability. Residual gases in vacuum system may influence SEM imaging quality. Minimization of errors, use clean room or laminar flow condition during sample handling. Analyze multiple regions of each particle. Cross-validate results using multiple analytical techniques. Regular instrument calibration with certified standards. Result statement is the chemical fingerprinting of space debris or return particle samples was successfully carried out using SEM, EDS, micro Raman spectroscopy and GCMS. The analysis revealed distinct morphological, elemental and molecular signatures that enable reliable identification of particle composition and differentiation between spacecraft derived debris and natural micrometeorite. The result confirmed that microscale analytical techniques provide an effective and accurate approach for source attribution, contamination assessment, and material characterization of space exposed particles. Thank you so much for your time. Allah Hafiz.